think we're close enough. 7:34 and 40 seconds, so I won't wait 20 more seconds. So welcome, everybody. You found your way into the February edition of the University Lowbrow Astronomers monthly meetings. At least it's February. That brings us closer to March. I'm Charlie Nielsen, the president of the club, seemingly forever. We have a few other officers, I think, yes, in Zoom and also in the room, and we'll probably get reports from them. But as tradition would have it, we have our speaker talk to us first, because perhaps some of you came for that and really don't want to sit around for our highly entertaining business meeting later. We may allow you to leave. So, but at any rate, and first I want to thank Vice President Don Foley for bringing us our speaker tonight. He did the recruitment. Excellent work. We appreciate it. And our speaker tonight is Jeff. Do you pronounce it McLeod?
Yes.
McLeod. And Jeff is a former Warren Astronomical Society president, a former observatory chair, and he is currently their outreach chair. During his time at Wayne State, he was a presenter in their planetarium while earning a bachelor's degree in physics and another in astronomy. Jeff recently started work in the aerospace sector, simulating missiles. Nowadays, most of his free time is spent working on his spaceflight simulator, which is a life-size recreation of a Gemini spacecraft that you can actually fly in. If any of you have attended our big astronomy at the beach event every year, you have seen Jeff's simulator set up there. He has to pull it on a little trailer and everything. You also might notice that there's a long line trying to get in there and watch it. So I've got to check it out myself. There's a line for some reason, I'm sure. In 1962, when John F. Kennedy said, "We choose to go to the moon," NASA was still very unsure how to actually do that. In this talk, Jeff is going to show us how it was made reality, as well as some alternatives and why they were not selected. He will talk about Apollo, the mighty Saturn V, and his aim is to inspire you. So with that, please welcome Jeff.
You want a mic gonna pick me up just fine?
Yes, that one.
Okay, awesome. Oh, all right, already. All right, actually, would you take this? And you can just pass that around.
Oh, sure.
That is the largest piece of the moon I could afford. It's 0.02 grams, something like that. All right.
Oh, I see.
Yeah, right in the center. So, let's get this going. Hopefully I won't break Zoom. All right. So you'll notice the date, 1962. We're gonna do an experiment. Who knows nothing about Apollo? Who knows a good bit of Apollo? And who knows just everything about Apollo? Okay, good. I want you to try to flush all of that out of your mind. You don't know the answer, because in 1962, we didn't know the answer. Okay? And to make it a little bit easier, I'm going to get into character. And let the 1960s just wash over me here. So you'll excuse me for a moment.
Oh, yeah. That was it.
And of course, our slide rule.
Oh, yeah.
This is how we got, or how we're going to get to the moon. And then my last piece of memorabilia, these are a little out of scope, but these are Soviet promotional Apollo Soyuz cigarettes. Pretty cool. All right, so we have a problem. We intend to solve this. And I really want this to be a meeting where we're going to try to collectively figure out what is the path forward from here. So also, it is 2:21. We are one day out from Friendship 7. John Glenn did 3 orbits yesterday. That's where we're at. We have sent 3 men to space, and we have orbited the Earth 3 times. That is what we're capable of doing, and the president wants us to go to the moon in less than 8 years. Okay, tough. And yes, this is supposed to be, how do I advance slides? Do I just click, or is there a keyboard?
There is a keyboard, yes, you slide that URL.
Oh, okay, perfect.
Probably there.
Yes. See, it,
Yeah.
oh, I can probably do that. Let's see here.
Yeah. That'd be very good.
This is supposed to be an overhead projector, so we wouldn't have all of that. That's why the slides wipe to the side. There is no color in this presentation. It's too expensive.
USB drive.
Nope, we don't have any of that. So a real quick overview of some of the things that we need to consider. So we have navigation, guidance, control. Those feed into our trajectories, our maneuvers, and then those are dependent or are going to lead us to our rocket design and the infrastructure we need to accomplish all of that. So it's not quite a direct flow from one to the next. They can feed into each other a little bit. So some clarifying things, navigation. This is knowing where you are. Okay. Guidance is where do you want to go, and control is how do you get there. That engine on the right is a command service module engine. So we're still in the early stages here. We're doing this very simply. So we're gonna make some qualifying assumptions, otherwise we'll be here a month. So first off, 2 dimensions, flat plane. We're not gonna consider the moon on a 5-degree incline. We're not gonna worry about that 3rd dimension. If we can do 2D, we can do 3D. Moon's orbit is circular, close enough. Idealized delta V requirements, okay? We're gonna learn as we go to see how good our math actually is, but for right now, we're gonna kind of use idealized minimal margins. We're gonna assume our rocket fuel tank to fuel ratios. This is a critical thing in the engineering side of the program. How light can you make the rocket? The lighter you can make the rocket, the better that ratio is, but there is a limit. Right now, we're just going to assume our engine performance is known. In reality, that is not true, but let's just say we know the engines that we're working with, because that's going to help make all these calculations a lot easier. No air resistance. Oh man, isn't that great? And then this is one because I was brought up in the modern era, but also to kind of throw you off your game a little bit. If you know some stuff about Apollo, giving you metric units is hopefully going to throw you, so you won't be able to kind of guess where we're going with certain things. So the things, because you guys are all program managers, government contractors, the people that are leading different aspects of this program, time is a major consideration. If we had 2 decades, we would be building a much different rocket. Cost, currently, not infinite. In the actual annals of history, they ended up liberating a lot of money post JFK's assassination. I often wonder, had he not been assassinated, would the program have actually continued? Facilities. Do we have the facilities to do this? Can we build them in time? Reliability of what we're designing, the complexity, and then finally, Newton's second law, F equals NA, weight is everything. All right. So the first thing we need to do is get to orbit. We actually know how to do this. We've done it 3 times. Holy cow. But the way I'm calculating this, just very crudely, but you'd be surprised how close it gets you to the actual numbers, is there is a speed for every orbital altitude. So there is a hypothetical speed at which you could orbit the Earth at 0 feet. And then there's a speed at which you orbit at 200 kilometers above the surface of the Earth. So we have a initial velocity, a delta V to get to that upper velocity, And so we just add these two numbers here. That arrow should be a little bit further down. Ends up being about 8.5 kilometers per second. That is how fast we need to get the rocket going to where it'll end up in a 200-kilometer orbit. Okay. Delta V is a number that we use in rocket science. Delta meaning change in velocity. So we're going to go from 0 to 8.5 kilometers per second. Most of the other stuff isn't actually important. Air resistance, it is a factor, but really not for very long. And when you're talking about getting into orbit, very little of it is the up, most of it is the over, getting horizontal velocity. Next thing we need to do is actually coast out to the moon. This is called translunar insertion. This is an early attempt of mine to solve this problem. This is actually for Kerbal Space Program, so the numbers are nonsensical and the names aren't even right. But you can't actually solve this. This is a three-body problem. That program doesn't use three bodies. It uses what are called spheres of influence. If you try to do this, you will go crazy. That is me. Now, because Kerbal Space Program is a game, you can use it, and it works in the game. I wouldn't use it in real life. What you need to do is simulate. So, simulation, very different than solving. We're basically using physics and we're going to run things forward in time. So we are just essentially using F equals ma. Now, this produces many different trajectories. We leave the Earth. We can swing around the moon, come back, and hit the Earth. We could swing around the moon and get ejected into intersolar space. We could hit the moon. Or we could whip around and come right back into the Earth perfectly. This particular one, don't do this. This is coming back retrograde, but it is theoretically possible. But then you're coming into the direction that the Earth is spinning, and you're really going to heat up. So how do we find the trajectory we want? We run hundreds of thousands of trajectories. So this is what we call a solution space, a solution map. So on the vertical, we have the delta V of that translunar insertion burn. And on the right, we have basically where the moon is relative to the spacecraft. So those are the only two variables that we have control over. So you can see, I'm going to walk off camera. I can't help it. If we launch with a lunar heading of 50 with not a lot of delta V, nothing happens. We don't get a capture. Even lower, we come back and fall into the Earth. We go too high, we get ejected out of the system, and then there's this ribbon in the middle where we have lunar impact, ejection off on the right, swinging back around, hitting the Earth. The way I set this up is if nothing happens to the spacecraft in 6 days, it just says nothing. And right in between hitting the Earth on the way back and hitting the moon is this beautiful free return. So we're going to zoom in, and it's still very hard to see. We're going to zoom in even farther. There is this razor thin line, and on either side of it is impacting a hard body. That's what we need to accomplish. So you can see basically as you go down, getting farther away from lunar impact means that you're in a higher kind of orbit around the moon. But that free return is razor thin. And it looks something like this. This might make a good Gemini mission if we can boost the Gemini spacecraft up and get it running for long enough. Gemini's a lot further along right now than Apollo is. They did actually consider doing a flight like this. It never ended up happening. So, we've coasted out to the moon. Oh, this is just the numbers on translunar insertion. So essentially, you need another 3 kilometers per second to get out to the moon. So since we've left the ground, we've got up to about 11 kilometers per second. This is what that simulation looks like. You can see the moon start to come in here. It's that capture point is when the moon's gravity is stronger than the Earth's gravity, and then it is released. You can see the moon's influence basically U-turns the spacecraft. And because we have no air resistance, when we loop around the Earth, we just get ejected out of the system. How long does it take to get to the moon? Anybody? 3 days? Good answer. A lot of people say 4. It's 4 because you go into orbit, you test out the spacecraft, then you do your 3 days, then you float around the moon a little bit, you do your landing, you do more checks, and so like launch time to boots on the moon is 4 days, but the actual travel time is about 3 days. And another thing I'd like to point out here is just how fast the spacecraft starts, and then just how much it slows down. So you can also see it's speeding up as it is literally plummeting back to the Earth. So I'll just let it start one more time here. That first day, it gets halfway out. I mean, that's only 20 hours. So that's the first day. Then the second day, you only get 75%. The last day, you're looking around the moon. So just to get a little bit closer, you can see just how close we get to the moon, and just some of the numbers here for what we call paraloon, or the closest approach to the moon, and that very hard U-turn. So there is a still frame. We are passing within 112 kilometers of the lunar surface and traveling around 1,500 meters per second. But this is in the absolute frame. The moon is moving. So that's really not the number we're concerned with. We want it in the lunar reference frame. So the trajectory looks like this if we basically hold the moon still. And so now I'm cooking past the moon at nearly 25 or 2.5 kilometers per second. So to be captured by the moon, we need to do another burn to slow down. So we're using that same orbital velocity calculation. How much do you need to shave off to be in a orbit? So our target orbit velocity is about 1.5, 1.6 kilometers per second. So you just subtract those, and we need just shy of a kilometer per second. Also, interesting because of gravity and radius, the actual orbit time for the moon is longer than the orbit time for the Earth. You go around the Earth every 90 minutes. It's 2 hours to go around the moon at a similar altitude, which is counterintuitive to a lot of people. All right, so now we're landing on the moon. We're doing the same calculation we did for our orbit in reverse. We have a orbital velocity at the upper altitude, and a theoretical orbit velocity at 0 altitude, the velocity it takes to go from one to the other, and we get 1.9 kilometers per second to slow down. And then getting back off the moon and back to the Earth is just those burns in reverse. It takes about the same to get off the moon back into orbit, and it takes about the same to get off the moon and back to the Earth. And because of aerodynamic braking, we don't need another burn to slow down at the Earth. We're going to use the atmosphere to slow down. So, is any of this reasonable with the equipment that we have? So here are some engines. I have 2 different formulas for estimating burn times, because if you crunch the numbers and your rocket has to run for 2 days, that's not going to work. So you can see stage 1, 200 seconds, stage 2, 500, translunar insertion, 250, 275. All of these are reasonable. 5, 7 minutes. Yeah, this will work. If they didn't, we would have to redesign these rockets. So all of those things have to happen. There's really no way around that particular flight plan. However, there are myriad of ways to build a rocket to do those steps and break the rocket into different segments. So these are just a handful of potential designs that we're going to go over. So first is direct. Let's just build a big rocket and just go to the moon. Real simple, 5 stages. So first 2 stages just get us into orbit. And the way we calculate this table is we work in reverse. So we start from what's the lightest spacecraft we think we can build to keep astronauts alive for 2 weeks. And so I'm estimating where I got 5,000 kilograms. Okay. I think so. I think we can do it. So we know the delta V from the previous slides. We take that, we put it into that formula in the bottom right corner, we solve for the masses, and we get a total mass on the very far right. We then plug that number into the next stage, because that rocket now has to carry that whole thing as if it was its payload. Do the calculation again, then we take that total mass, put it onto the next stage, because now that one treats that as its payload. We go down and down and down through the 5 stages. At the very bottom right of the table, we get a 4.4 million kilogram rocket. We've launched one Atlas orbital flight that weighed 120,000 kilograms. This is orders of magnitude larger. This is potentially an issue. I'm only going to go over the first stage, but realistically, we need to do this for every stage of every plan that we're going to talk about. But let's just look at this first stage of this massive rocket that we're talking about. So we have 4.4 million kilograms. We can calculate the force that that produces on the ground and get an estimate of how much thrust we need to lift it. We don't want a 1-to-1 ratio. We need more than that because we got to get this sucker moving. Okay, so we know the thrust of our F1 engines, and so we're going to need 8 to get this thing moving fast enough. Now, in order to fit 8, the diameter of this rocket needs to be at least 15 meters. That's pretty darn big. We currently have no facility large enough. We don't even know if we can make tanks that large. We also know what liquid oxygen and this RP1 kerosene weighs, so we have a density there. We also know what our combustion ratio of those 2 liquid propellants is, so we can calculate our fuel mass. We can plug that in. We can then figure out the volume, and we can figure out how large these tanks need to be at 15 meters in diameter. So, you know, you guys don't need to do the math. You just need to know what's happening is that this first stage is going to end up being about 92 feet tall. 92 feet. That's my only feet. 28 meters. Is big. It's very big. This thing is taller than a Titan rocket on its own. So we need to do that for every single stage and see if it is reasonable. So let's break this down a little bit differently. So now we're doing the translunar insertion and the lunar orbit capture on one rocket instead of breaking those into 2. We run the calculations again. We saved a little bit of weight, but it's still 4 million kilograms. So von Braun really likes Earth orbit rendezvous. Once he was kind of convinced that direct was not going to work. It's called the Nova. It's massive. So Earth orbit rendezvous. Let's build 2 rockets, connect them in Earth orbit, and then send them to the moon. So we have 2 separate rockets there. And basically, this is going to get into orbit. And that section up there that's labeled translunar insertion, they're going to then dock with each other, and they're going to go to the moon. So you can see by the masses on the right in the middle there, 1.8 million kilograms for the one rocket and 3 million for the other one. Somehow we really didn't save much weight. We ended up with something heavier overall, but it is two smaller rockets. This is potentially workable. However, we need to design two independent launch vehicles. All the engineering of designing a rocket 2 times over. Don't know if we can get this done in time, but there is a workaround. We could do a fuel transfer. So lighten up one rocket, make the other one a little bit heavier, and then transfer fuel in orbit. So now these two rockets are the same design. However, now we not only have to dock in space, we have to move propellants from one rocket to another. We've never docked in space. Don't even know if we can at this point. Also, vehicle turnaround time. I mean, how quickly can we launch these things? You know, if it takes 2 weeks between launch operations, that's going to be a problem. Can we build a whole separate launch facility and launch these things hours apart? Unsure. But that average weight, if I go back, we're down to 2.4 million kilograms. This is a tremendous savings in weight, and a little bit of saving in complexity being the same time. Now, what about lunar surface rendezvous? Let's send 2 craft to the moon. We'll send a lander with men, and we'll send a refueling craft. This also saves us some weight. You can see the one rocket ends up, the one with men on it, 1.8 million kilograms. And the one with just fuel, 2.7. However, precision landing right next to a fuel depot. If you miss the landing zone by longer than your fuel pipe, that's a problem. Again, we have no idea if we can make precision landings on the moon. Similar but slightly different would be a dual lander. Let's send them in one craft and come home in another. This is interesting because they are doing slightly different jobs. So why make one craft do the whole thing? Design one craft just for landing on the moon, design another one for coming back. You get pretty good savings on weight, but again, this is designing 2 completely independent rocket systems. You need to land walking distance away from your return craft. Could also pose a problem. And finally, probably the most harebrained of all the schemes, lunar orbit rendezvous. This is, let's pack everything on one craft, but separate them in lunar orbit, have a dedicated lander, come back up, re-rendezvous in lunar orbit, and then come home. Tremendous weight savings. We end up with one rocket that's 2.8 million kilograms, so still way bigger than anything we currently have. However, it's only one rocket, but it's very complicated. You've got a lot of independent motors, you've got a lot of maneuvers to perform, a lot of stuff that we've never done. And then there's some variations on this as well. We could extend that 3rd stage, make that 3rd stage do the translunar insertion and the lunar orbit insertion. It saves you a little bit of weight. However, in reality, making that stage larger and staying with it means that your maneuvering tanks need to be larger and some other systems end up growing, and it could end up nulling out the savings. This is what I call super command service module. What if you just had it do everything? And this actually works against you and ends up being heavier, so don't do that. How about split lunar orbit rendezvous? Instead of sending these 2 craft on one rocket, one big rocket that we're not really sure we can build, we can get these things down to something only 10 times larger than a Titan II missile. Now, again, this involves rendezvous, but we kind of already had that issue. But again, can the launch complex handle multiple launches in quick succession? So those are the designs that are on the table for us, but I wanted to just go for broke. Say, why bother with this small little short duration mission? What if we wanted to do 100 US tons in a 2-stage reusable rocket? Why bother with 5, 7 stages, multiple rockets, all this stuff? What would that look like? And let's just call it the Astro boat. It would look something like this. Okay, 2 stages, super simple. That picture in the middle, that's the upper stage, and that by itself is like 120 feet tall. You can see the picture all the way on the right. This thing can hold like 50 people. 50 people to the moon. So let's crunch some numbers. We have the booster, what I'm calling the boat, the upper stage total. And then if this thing is empty, 100 tons or 150 tons, the bold one is the only one we're really concerned with. That first stage gets about 3.5 kilometers per second. The upper stage about 7 kilometers per second. But if you want to reuse it, each of those stages needs to reserve about 1 kilometer per second.
Jeff,
Yes.
is that microphone still on? And if it is, could you?
Yes.
It's interesting. I noticed we've got 11 chat things there. I'm looking at it on my phone. I only show 1 chat. I don't understand that.
How do I know if it's on?
There it's on.
It's on? Okay.
But then
Perfect.
chat said he thinks that we're switching between microphones. Front and
Oh, it's jumping.
That's
Okay. So each of these needs to reserve about 1 kilometer per second to actually land back on the Earth. So 11,000 meters per second is actually just enough to like get into orbit, and it's empty. So it can't get to the moon. We need to refuel this thing in Earth orbit. So how many does it take to refuel it for a total mission? About 12. But each of them is refuelable. So you don't actually need 12. You could maybe have 4, and they go up, they come back down, they refuel, they go up, they come back down. So one of these has about 7.4 kilometers per second of usable delta V when fully loaded after the 12 refuel it. However, we need 8.7 for a lunar mission. So we still don't have enough. So you have to send another partially fueled one to the moon with you in order to get home. So how many more is that? About 8. So we're at approximately 21 of these rockets to do 1 lunar mission.
Maybe we can get a volume discount.
I'm tempted to say the math isn't mathing. Also, this is a concept sketch of our lunar lander. This thing is about 24, 25 feet tall. The Astro boat being 120. You can see, I'm going to break character for a second. I think that's Apollo 16 or 17. Kind of landed on an angle. The moon doesn't necessarily have a lot of flat spaces. And now you want to land a 100-foot tall rocket on the moon. And then there's just a comparison to a concept of the Saturn V. And I have no idea what that thing all the way on the right is. Some weird tugboat that they've been working on. So navigation, how we're going to figure out where we are. We're doing this with a network of radio satellite or radio towers. We don't have them everywhere, so we actually do deal with communication blackouts. We also have the ability to navigate the way that early sailors navigated. We can actually use the stars. So from the Earth, we can look to the moon, look at background stars, and triangulate where the moon is. And from the spacecraft, we can look at where the Earth, Sun, Moon is, and that will actually solve for a singular point in space. It's nice to have redundancies. You know, the radar's telling you one thing. It's nice to have another measurement.
Especially a light one.
Yes,
Watch the do the,
just a little bit of time and practice. So that's essentially the presentation. Before I go into the hindsight, any ideas which one sounded the best? Any opinions? Direct? Who's for direct? Just massive rocket. Yeah, no. Earth orbit rendezvous, refueling in orbit, or docking in orbit? Could work. I think you guys know lunar orbit rendezvous, right? When you really dive into the math, and as they did in like 63, it kind of became apparent that lunar orbit rendezvous was going to be the only way that they could get it done in time. Had they had more time, they probably would not have gone for lunar orbit rendezvous. They would have gone for a multi-rocket system and probably made something simpler. But being able to do a mission with one rocket, huge selling point. If you think of just how many Saturn Vs they had to build for the program, if you were to go with an Earth orbit rendezvous, you would have gotten half the number of missions. So we would have been lucky if we had 2 to 3 successful landings on it. So it's just to show you I'm not making up everything, that these calculations are tethered to reality. There were numbers assigned to the Nova rocket, and let's see, so total mass down here, I hit it to within 1%, because physics is physics, essentially. And because the thing never existed, they were also just kind of guessing. But this thing is massive. You can see it's got 8 F1 engines on the first stage. I believe it has 5 on the second, whereas the Saturn V had 5 J2 engines, not F1s. So lunar orbit rendezvous delta Vs, so that translunar insertion maneuver, my estimate 3 kilometers per second, the Apollo program averaged 3.1. So pretty darn close. And I would venture to guess it's because I was doing 2 dimensions. They had that third to contend with. Apollo 11 lands almost perfectly on the equator, but some of those other missions, when you want to land in the lunar highlands, in order to get there, you have to follow a slightly different trajectory. You cannot use a free return trajectory like we showed here. That was the safest trajectory for the early missions, but once they gained confidence, they went for non-free return trajectories. You really want to have reliable motors if you're going to put yourself into a situation where if things go wrong, you cannot get back to the Earth. Lunar orbit insertion, almost right on, 1%. Descent, a little bit different. My guess is, my calculation is overly simplistic. The profile of a real lunar descent has very distinct stages of deceleration and coasting at a certain altitude and all this stuff. But still, 10%, I'm perfectly fine with that. Trans-Earth injection, also right around the same, and then like total time and stuff like that. So weights, how well did we hit those weights? Pretty well. So total mass there, the Saturn V rocket weighed just under 3 million kilograms, and we were estimating 2.8. First stage, so I made another simplification. I did orbit in 2 stages and then to the moon in a 3rd stage. Apollo, they did 2.5 stages to orbit, and then the 3rd stage also got you out to the moon. So they shared that 3rd stage for 2 different maneuvers. So that affects how I'm distributing the weight, but I just didn't want the added complexity of distributing weight through multiple burns. So that's probably where that error is coming from, because this really is just a simple physics problem. There's no getting around it. You need this much energy to do these kinds of maneuvers, and it's going to end up weighing what it weighs. Essentially, rockets are Newton engines. They push things out the back, and it really is just the weight that you throw in the other direction. That is the rocket equation. And then finally, burn times. These are a little bit harder to estimate because they really come down to the performance of the engines themselves. But I still think we did fairly well. Nothing crazy. So these are the two books that I highly recommend if you're interested in Apollo. The How Apollo Flew to the Moon is like my favorite book in the world. It goes into every aspect of Apollo. It breaks down all the different phases of flight. It has stories about every single mission. Apollo by the Numbers, you can get free online. This is kind of dry. It is just a treasure trove of data on the Apollo missions. So if you want to know how many pounds did Alan Bean lose on his lunar flight, it's in there. A lot of them lost 4 to 8 pounds on missions. So this is where I normally work. I'm a Gemini guy. I don't even work Apollo. I work on the Gemini simulator. So if you've not seen it, I try to bring this to as many events as possible. And if you'd like to have me back, I have a presentation that is both on Gemini and my Gemini, how I built it. What's that? Talk to me afterwards. I'm pretty open. So this is just a quick snippet of me flying around the moon in the simulator. So Gemini did not have a heads-up display. That's something that just makes flying a little bit easier. Also, Gemini never went to the moon, but it's just fun to fly places.
We got a question in the chat about what does the asterisk by CSM Fuel mean?
Oh, let's go back. I'm sure I have it in my notes. Let's see. Oh, yep.
One forward.
Did I click it? Whoops. Okay, what am I doing?
CSM fuel.
Oh, let's see if I center view. Why did I put that asterisk there?
Because it's an asterisk.
Oh, it might have to do, so Apollo 13 kind of screwed up some of the numbers because it was supposed to land on the moon and it didn't. So that could be, also some of the command modules didn't go to the moon, or, didn't have other components. Yeah, I don't see an obvious answer in my notes here. If I figure it out, I'll get back to you. Yeah, there's a reason, because I put it there. Good question. Any other questions?
So we didn't talk about the infrastructure. all the stuff that I think I need.
Yes, so there are some other fantastic books on the subject. They were looking at, basically there was a facility that they could buy in Huntsville, Alabama, that could do a 30-foot diameter fuel tank. They had the ceiling height, they had the crane infrastructure, they could move these things around the building. It had river access that they could barge these things to Florida. And going to the Nova at a bigger size would mean that facility will not work. We'd have to build one up from scratch. And that was actually kind of pivotal in the deciding factor to direct is not going to work. They bought the location in Huntsville. That kind of solidified the Saturn V. Way easier to buy something that is half done than to try to build something up from scratch, for sure. And then the launch facilities, I don't know as much about, but I can tell you with no uncertainty that building a launch facility for the Nova would have been much more complicated than for the Saturn V. If you've seen the crawler that they have for moving the Saturn V, I mean, you're talking about something that weighs almost double. The vehicle assembly building, like every aspect of the program gets more complicated.
Certainly the safety radius would have to.
Yeah. Yeah. And they did consider even larger rockets for different things, but they were gonna sea launch them, if you've heard of like the Sea Dragon and stuff. Yeah, I believe I also heard one of the reasons that they scrapped the Nova idea was that had it detonated on the first stage, it basically, they couldn't be far enough away from it. It would be such a large explosion that they would have to like relocate people, and yeah, it was just too big. All right, I'm gonna disconnect.
There might be questions.
Oh, I'll let you handle that.
Let's see.
Yeah, I'm taking that with me.
We don't have any more questions in the room.
Can you tell I'm not a fan of SpaceX?
Did adding a rover change the fuel or mass considerations much?
It absolutely did. However, the command service module, lunar module were so well designed with sizable margins that they were able to allot for it. You kind of each mission profile is very distinct, so you sacrifice some things in order to carry a rover. The rover was also fantastically engineered to fit into a storage compartment that already existed on the lunar lander, and yeah, and not weigh a lot. Yeah, so cool. But yeah, I mean, the other thing is that it cascades down the chain. So famously, the Saturn V first stage has a single bulkhead between the two propellants. And that was to save weight, because what ended up happening is the third stage kept growing. If your third stage grows, your second stage grows, first stage grows. And it was like, well, the first stage was already 90% done. It's like, we can't change certain things about this. And so they, in some ways, that first stage is not as robust of a design because of that single bulkhead. They had to do some really interesting thermal things to make it all kind of jive. So it's even worse when you're talking about the lander. You add, I should have done a study on it. You add 100 pounds to the lander, you end up adding 10,000 pounds to the entire rocket. And so when you get to those upper stages, I mean, they're measuring things out to the gram. And so one of my when people talk to me about like, oh, was the moon landing real? I like pointing out that you don't spend millions of dollars designing the most complicated lightweight color TV camera ever made at the time if you're faking it. If you're faking it, you can take the heaviest camera that you want. And so yeah, like the hardware that they were actually carrying is fantastically scrutinized to the nth degree, because weight is so important.
So that brings up how much more fuel they had to carry for Shepard's golf equipment.
Each astronaut was allotted a certain poundage of kind of whatever they wanted, and that's what he spent his on. Yeah.
Any other questions?
Did they allow for the weight of the moon rocks on the way back?
Absolutely, yeah. And most everything is thrown out. So one thing I kind of didn't talk about is, you know, I got these little model rockets. This is like the direct lander. This is essentially the command service module. You know, the little lander that actually goes on the moon, you leave the whole descent stage behind. And then when this comes up and the astronauts get out of it, they huck this back at the moon. There was a handful of flights where they brought spacesuits back, but for the most part, when they would redock, everything they didn't need, all the human waste that had currently accrued in the command module and the lunar module is all packed into the lunar ascent module and then jettisoned. And so then you got rid of some weight, you can bring more weight back on. But yeah, every pound counts. But thankfully, the US cared a little bit more about the scientific endeavor than the Soviet program seemed to be concerned with. And so they really wanted to actually have something to show for these missions. I mean, they definitely were politically motivated. However, there was an engaged scientific community that was able to get them to do some real science while they were there, which really makes, you know, everything more worthwhile. And so there's only several hundred pounds of lunar samples that were returned over those 6 missions. That's it. And that's all that's out there. We've had, there's a fantastic lunar geologist in the area, and she works with those lunar samples. We're still using them today.
I actually worked in the Apollo program. I worked on Apollo 17.
Really?
But I'm the Apollo lunar service experiment back in
He's who we need to talk to. And was weight a consideration? Yeah.
My claim to fame is much less than that, but I did see Apollo 14 left off.
Really?
Yeah. Yeah, from Titusville across the
Indian River.
Yeah.
The thing I think I remember the most, it looked different live.
Yeah.
One thing,
Especially the flame itself out of the engines. It had much more of almost a candle look to it. It was really weird. But what really got me is it lifted off. It was already into a cloud bank and starting to pitch a little bit, and there's no sound. Because we're like 4 or 5 miles away, right?
Yeah.
Nothing. And then before you heard the sound, everybody started looking at the ground. Because you could like suddenly feel something in the ground, and then you heard the rumble and
Wow.
felt it. But you could actually kind of slightly feel it in the ground before you heard it. That was really cool.
It does travel faster through Earth than it does air.
yeah.
I was there for the second to last shuttle launch, and they scrubbed it, and I had to go home.
Yeah.
So I've never seen a launch.
Do you remember, all of a sudden I forgot, do you remember what percentage of the US budget at the max?
Yes, I don't spread it around, but I want to say at its peak, it was around 5%. You know, it was never 25%. Yeah, I think it's only around 5%. But fact check me, get on Google.
Curious what this gentleman's goal is. And
She's talking to you.
you're about it.
I was a junior engineer just at a college. So I had a very, very minor role. I mostly wrote test procedures and did tests of thermal vacuum chambers, shakers and all kinds of stuff, experiments. I did design one resistor value in the power control unit that regulated the voltages for the experiments. But most of it was just.
So the vacuum would be for inside the space.
Well, what we did was you had to test the equipment. So there's this huge vacuum chamber and you would put the experiments into the vacuum chamber. When you pump out all the air, simulate the environment. And you have an arc lamp simulating the intensity of the sun. And you have to operate the experiments for a whole lunar, for a whole lunar day, month, to make sure it will operate. Yes.
And as far as I know, everything worked fine. So,
Yeah,
you did a-
16, they tripped over the heat plug cable.
yeah. Mistakes were made.
Plus some other.
All right, okay. Thank you very much.
Thank you guys so much.
So, Jeff had requested a small size club T-shirt is our little gift. And wouldn't you know, I don't have any smalls left. So we're gonna send you one from Traverse City where our treasure is. Now, do consider they shrink a little bit when you wash them. Okay. Can you tell me how you do that? Yeah, there you go. So on to, yeah, so if you can send me an email, let me know where we can ship that to, and then we can talk about your next appearance too.
Sounds great.
Beautiful. Okay, I've just got a couple of things just to remind everybody that next Wednesday, we're going to hopefully make an appearance at Glen Cairn Elementary School in East Lansing. Also ironic, we're playing a team from East Lansing as we speak here in Ann Arbor, the Michigan State game. We do, thank you very much. Do have a pretty good number of people going to that, so I think we're covered pretty well for it. So we just got to hope now that the weather doesn't mess us up. Right now, the forecast is good as far as traveling up there, so let's hope it stays that way. We also scheduled a Michigan Math and Science Scholars event for July 21st, as I recall, rain date of the 23rd. We were working on one in March, but it was hard to find help with it, and also conflicted if we do a Messier marathon. And I think Shannon kind of portrayed to it. Are they sure they really want to do it in March? So anyway, we kind of all mutually agreed we're going to cancel that, and they're probably going to reschedule in probably, I don't know, April or May or something. You think they will? Or? Okay.
So this is SAS. the
Yeah.
state,
Oh, okay.
And I don't know, it's not clear to me yet how many of them are here in the spring. Because several of them are doing Master 461 at Kit Peak. Like the entire executive board is going to Kit Peak, so.
Wow.
They're hoping to.
Okay. We also scheduled for March. Does anybody remember the Tecumseh Parks and Recreation? I thought I was gonna spit it out, but I didn't. Anyway, we've scheduled a reappearance there. I think Jeff already said he was gonna go. Yes.
It's like late.
Yeah, that's what I was thinking, like last week of April, somewhere in there. Anyway, I'm gonna be after people for more help on that one anyway. But like I say, we got a couple so far. And actually, that is really a nice venue. The people are nice there. And it is considering less than a mile north of downtown Tecumseh. it's darker than my yard is. And I'm not too bad out on the, way out on the west side of Ann Arbor. Part of it, I think, helps too, is we go behind this building that just happens between us and downtown. And I think that shields us a bit, but especially last year when up there, I got some better shots with my C-Star than I do at home on the best nights at home. I was really impressed. And when again, you see, consider where it's at, it's rather amazing. But anyway, I recommend going to it. It's fun.
I should also,
Pardon?
Is that?
It's at Tecumseh Parks and Recreation. It's actually called the A.J. Smith Recreation Center. It's right on that north-south road going into Tecumseh on the east side of the road.
The presentation.
We're just setting up telescopes.
Yep.
Yeah.
and they do have bathrooms to use.
Yeah, yeah.
There are restrooms to use, which is really, really nice.
Also a big benefit. Yes, good point. Couple other quick things. A few days ago, got some more award pins from Night Sky Network. This year's editions look like this. Kind of neat. You can't see it very well. It's got like a really glittery kind of background to it. We get 3 of these about each year, and they're really intended for people in the club that have done the most outreach. So what I usually do is get the officers together. We look at all the reports we did to see who showed up for what events, whose name showed up the most. And then I temper that a little bit with, okay, did the same person win 2 or 3 in a row? Is there somebody that participated maybe slightly less, but they're still getting into it? We might give it to them just to reward them for getting involved. So anyway, we're going to be working on that. And when I put those in there, I remembered I still had the ones from last year. So we actually got 6 of them. In fact, that one's kind of cool. I think that little moon thing moves or something on there. It's not doing it now, but anyway. So that'll be coming up. And just one other quick thing I also got the other day from Night Sky Network, this NASA calendar. I really don't need it. So I was thinking, should we do some kind of contest and give it away? Or what do you think, Jack? Could we, where do you go?
You need a calendar here?
Oh, there he is. Pardon?
You need a calendar here?
Well, that's a thought, yeah. Either that or the observatory, but that's a thought. Maybe we could give him, yeah. One. Yeah, I'll ask Austin if he can use it. It's actually, it's got some decent pictures and stuff in it. So forth, so. Right, so look at that. Anyway, okay. That is all I've got, so I'll move on to other officers, starting with Ken. Thank you for doing the minutes again.
I've contacted Dr. Reno, but I have not heard back. So, Dr. Barshot's suggested him as a speaker, so working on that. I've also emailed today 2 more potential speakers. I'll try to reach out to them.
I was gonna say, he sent a thing for, was that just today?
Yesterday or today.
Yeah, okay, it was recent though, yeah, okay.
So, it's okay. So that's all. We're working to line more speakers. And we found another one today. Well, that's
Yeah. See, I get these easy ones. That was one of them. What was it, last month? Jim Shadlowski just all said, well, I got another one for you. Exactly. Okay, Don. That was fast. Let's see who else we got in the room. Jack.
It would take a couple of minutes. I got a few things to talk about. Try and do this quick. Things that we had some discussions about. I gotta use that.
All right.
How's that? Can you hear me okay? Okay,
Yep, we're good.
I'm just gonna put this, how do we show this on the,
It's on there now.
is it on there? Oh, no, wait, what happened? Okay, okay.
A lot of focus is on.
Oh. Did I focus back on?
That's
There we go.
Should do it manually.
Yeah, for some reason.
That's not the right one. So it's freeze on.
Whoops.
We should see if we can zoom it.
Yeah.
Probably gotta make sure that freezes off. You're frozen now.
Yeah.
Wolf vision.
I don't
know what happened. Last time it worked perfect.
Yeah,
This one.
yeah, this thing's always been.
Oh, darn.
Fall. That's on right now, it's frozen, other one more ahead. There. Wow. It's still frozen.
Yeah.
You did the freeze thing.
Oh, what else is it? See, this says autofocus, focus on this one.
Yeah, and so I
I would
would
see you can turn it on and off, but you can't.
Autofocus is off.
on, okay.
So you have to turn off the freeze.
Okay, try this.
There.
Oh,
Aha.
all right, hey.
See, it takes a team.
Yeah, all right, I'm gonna do this real quick. First of all, that's the new satellites that are going up for all you guys in astrophotography and all of our observers. The new ones are 700 square feet. And I'm gonna do this real quick. The company that is doing it is gonna do another 200 of them. And I'm not gonna, this, by the way, came out of Barron's Magazine last week. And I'm not gonna go around and go through the whole financial thing, but only important things, 700 square foot antennas, 250 satellites, and the company has FCC approval and funding for it. So that's gonna be fun. And I'm just gonna go real quick because I'm not gonna go through this whole thing. And let's just go here. Here's what you're gonna get. Starlink's gonna continue with some more, another 750. The new space mobile platform's another 20 with a maximum of 250. And then, whoops, where did it go? So 250. Now Amazon's gonna come up with their 3,200 new satellites. So in the next year, couple years, you're gonna see a lot more. So the guys in astrophotography, they're working out how to pull the tracking out of the photographs, get rid of the lights and this and everything else. Continue to work on it and expand your knowledge and creativity because you're gonna need it. Okay. This, by the way, like I said, came out of Barron's. You can go to your library and read it if you want. I'm not going to go through this whole thing here because that's not their intent. Here's the big project we got going on. Okay, some of you may have seen this already. This is the Henry Ford. This is going to be the Ford Astronomy Club conference and swap meet. Now, I wonder if I'm just a little scared to do this. Oh, it is working. Oh my goodness. Oh, okay. Thank you. Well, this make a little more sense. I know some are very familiar with it, but we're going to go there again this year. I've got a table reserved. Another club member, Mike Hagan, has got the other half. And the point I'm bringing up about this is something that some of you are well aware of. What we've tried to do here is, I did talk to some of the officers and other people. We have a few things out here, like this mount that we had in the observer. It's been out there for like 10 years. It's the 2-inch diameter mount. And we got to go ahead, we're gonna bring that there. And then I also have the parts for the old Coulter mirror assembly. This is the 4.5 inch diameter Coulter mirror. Down here in the bottom. We're gonna sell that there. Some people said sell it for whatever you get for it. These prices aren't exact because I'm not sure what it'll be like out there. But if I could sell for 75 to 100, I would. If I get 100, 150 for this, yeah. But with it would also come, whoops, sorry about that. The original secondary mirror, which some of you are aware of. That's the original 4-inch mirror. Let me see if I can get it underneath here. Well, yeah, let me see what happens here. I get, oh, there we go. Oh, yeah. Okay. Was that the old 17.5 inch Coulter we had years ago? We've had the stuff. Yeah, if you want to try and re-zero it. Yeah, okay. But it's still good, along with I've got the 2-inch holder that I'm selling with it too when we sell this out at what's it called, over at Ford Swap Meet. You might remember that. Some of you might. That was out of the old Coulter. It's things like this we've had in there that's we're trying to get rid of. It's time. For those of you that forgot what used to hold the Coulter together, that was the secondary holder. That comes with it too. So if you're gonna go out and build a telescope, you need a 4-inch mirror, 4-inch secondary, you're welcome. Now, that, just one other quick one. By the way, if anybody in the club wants to buy these, let me know.
They could be yours right now.
Yeah, I think. All right, here we go. I'm gonna do this real quick. All I'm doing here is we've got zoom out. Yeah. There we go. Okay. I'm gonna go real quick with this. This is our data collector we have in the observatory for temperature and that. As you know, we put another heater in there because we're trying to solve the problem when we get this below freezing out there by the observatory and that. And it looks like we did hit last couple weeks, we hit a -9 and a -5, and the dew point was a -15. Okay. According to our data, we got the inside temperature in the observatory got down to around 15, but it stayed back above 32, and it was probably in that 15-degree area for probably about a day, based on these temperature readings and that I got from local antenna out there from, wonder what you call it. Forgot the name of the group that does it. But that shows that that's working, and that's nice because you remember years ago, everything got frosted in that observatory. The blue line is the humidity, red is temperature, green is dew. And these numbers here came from the data. I'll tell you in a second. Just because I know people are going to wonder where you got that from. Weather Underground, they have a cell out on Dexter Town Hill Wall, Dexter Town Hill Road, and North Territorial. So that's about a mile from us, 1.5 miles. So it's fairly accurate as far as outside temperatures with the wind blowing. That -9 temperature was even colder. And as this dew point goes down more, it means that cold will travel. If the dew goes up and they touch, that means you get moisture and rain. So that's not going to happen. So yeah, it gets cold out there. Most of you know that because you've been out there before. Other than that, those issues and the Ford Astronomy Club. Oh, and one thing we talked about also real quick. On Ford Astronomy Club, we in the swap shop, maybe in 2026, Maybe the club could get a table, and if club members have things they want to sell, they could bring it there to the table and sell them. Think about that. We'd have to buy the table, and you get one admission with the table. So if you did want to sell stuff, you want to bring it out there, you'd have to buy admission, but still it could help club members if they wanted to sell some of their astronomy stuff or telescopes or parts or books or whatever.
I might do that.
Yeah.
Yeah, I got some stuff that I haven't used for so long and should have somebody else see if they can use it.
Well, the only other thing I'm thinking about is looking at the observatory again. We do have a 6-inch f8 cave telescope. Ken Rubel did a lot of work on fixing it up and cleaning it up. Later on, we got a new mirror for it. We got the mirror recoded, and that's the original cave mirror in there. So that hasn't been used, been sitting out there for 8 or 9 years or more. That could be another thing that we could maybe sell at the swap shop too sometime. Doc, go ahead.
That has the closed. Is that? Closed on?
No, it's,
I thought that was the.
Yeah.
Okay, that's all.
Yeah.
There's.
Yeah.
That was 6, right?
no, that's, yeah.
Yeah, I didn't
Yeah.
realize it was.
Yeah.
Matter of fact,
But I think we should.
this is the one we're talking about that, Ken Rubel did an awful lot of work and not that one, I'm sorry. It's this one here. This is the one. He did a lot of work, cleaned all this up and set everything up really nice. And then we got a new, we had the mirror recoded for it and that. And, that might be something else we could talk about, getting rid of later too. Nobody's used it in years and it's just sitting there.
There were 2 other.
Yeah.
The case is best of the eights.
We have 2 other.
Yeah.
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 Getting rid of one of them.
Ed, like to point out though, is like if you've not been to the Ford swap meet before, it's more than just a swap meet. They've got lots of interesting talks and seminars, 2 tracks going on at the same time. So for $5 or $10 or whatever to get in, it's actually a pretty fun afternoon.
Yeah, I didn't focus on this a lot, but that is correct. They have a general astronomy talks. They have some technical talks. Club member Clay Klessler is giving a talk on telescope making. Adrian Bradley is doing a thing on astronomy versus pretty pictures. So that might be
That's 2
interesting.
Lowbrows right there.
Yeah. So yeah, that's true. So that would be some other things you may want to go and listen to those. And you can look at the swap meet too. So think about hit it, taking up everybody's time. With that, I'm going to turn it back over to Charlie.
I don't see any other officers in the room. Or do I? No, he didn't. That's a good point. Yeah, and I don't think he's in the 6 hours.
Yeah, it's after.
I'm here.
Let's go. Jeff.
Yeah. The only thing I really got to add is we had a little bit of movement on the Young Astronomer page. That thank you, Jack, for bringing that stuff to our attention. I think next month the domain, the lowbrows.club domain, is going to be renewed, and I checked, and we do have 1 more year on the hosting that we have for the new site. I haven't heard anything from ITS regarding the AFS retirement or the web service retirement. So no news is, I guess, good news, but we know it's coming sooner or later. We are now the only non-academic group that exist in AFS land for websites. So I got to think that shoe's going to drop at some point. The only thing I had to bring up was just to ask if we needed carpooling for the Glencairn event. Because I got some empty seats in the van and I am going to be taking that large ladder out there. So
Yeah, why don't you send an email about that?
yeah, I figure we can follow up, but just to put it out in the open, if people are planning on going, there's probably some carpool capability.
Yeah. I know I thought about that, but I'm probably going a different way because I'd be going like
Yeah.
Weston up 127. If anybody would go with me, it would be like Ken, but I don't think Ken is going, so.
Well, last year we met over at Jim's place and just piled into the van, but I got seats free, and if anybody needs a ride, I'm coming through Ypsilanti to go to Lansing, so we'll be passing by.
Okay, thank you.
Yeah, email will be a good thing.
Yeah,
Yeah.
send email.
Cool. That it, Jeff?
That's it for me.
Okay. I see one more officer, Brian.
Nothing other than if you read the newsletter, you saw that I put through our C-Star through its paces and wrote a review for the newsletter, and so I'll be getting that back to Amy this week, and it will be available for checking out by members. And so I highly recommend that people read the article and check out the fantastic little digital telescope.
Which reminds me, we've got to do that exchange because we were gonna take that to Glentown
Yep.
Wednesday, so. Okay,
Oh, so
Does
you
anybody-
do you want me to give it to someone else other than Amy?
was Amy?
Amy's online.
She
Yeah, I'm
showing?
here.
Oh, I didn't see, I'm sorry, Amy.
No problem.
I didn't see you, Melissa, where you at? Oh, there you are.
Are you heading to Lansing, Amy?
I am. I might already have a ride, but I might take you up on that. Yeah.
Okay, I was just thinking about the C-Star.
Yeah.
I could bring it then. Yeah.
Yeah, if Brian
Yeah.
brought the C-Star, or got the C-Star to you, then that'd take it care of it then for Wednesday.
Yeah, that works out.
All right, I'll get it to Amy by Wednesday.
Okay.
Sorry, I didn't see you there, Amy. Do you have anything else to report?
Nope, no report.
Okay, thank you. And I also apologize for the Zoom audience for not noticing the audio problem earlier. It was really odd because I think occasionally Jeff might have been hitting the top of the screen and it brought the little Zoom thing down and I saw this like 13. And I said, is that 13 chats? I don't think that's good. So I fired it up on my phone so I could see what they were before I interrupted them. My phone showed there was no chats. So I thought, well, maybe it was 13 participants and I didn't see it right. But it really was 13 chats. But yeah, my phone would show a different number. I noticed all along. Like a new one came in, it showed it, but it didn't show the other ones. But anyway, I apologize for that. So lessons learned.
We'll find you.
Anxious about this thing, so. And we do have the recording, so hopefully that came out. If somebody missed the beginning part, they can always catch the recording.
Yeah, I think everything's pretty good on the recording, so.
Cool, cool. Does anybody have anything else? Okay, just a reminder, it looks like they are observing up at the telescope upstairs. So I welcome anybody if you want to take a look out there. I know Jeff, I think, has only seen it once, so he's gonna go up there for sure. Last I knew, the sky was clear. And people are still going back and forth, that's a good sign. So, with that, I'll entertain a motion to adjourn. Support? Is anybody opposed? Thank you very much.